Hello viewers, Wagadaruna taking you through the story of A-Level Physics Paper 2, and this video I'm going to go through the topic of electrical energy and power. So this topic is under current electricity and is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So before we start, let's first look at the course outline of this paper of Physics Paper 2. Now, Physics Paper 2 is divided into 4 parts. The first part is Geometrical Optics, where 2 questions come and the student must answer 1. So those questions come from these topics. The next part is Physical Optics, where 2 questions come from these topics and the student must answer 1. The third part is Electrostatics and Electricity, where 3 questions come from these topics. And also the fourth part is Magnetism and AC, where 3 questions come from these topics. So here it is you to choose. You can choose to get 2 from here and 1 from here to make the 5 questions. Or you choose to get 1 from here and 2 from here to still make the 5 questions. So any of the 2 options is okay. So we already covered electrostatics and capacitors. Now we are on current electricity. And like I told you in this video, on this YouTube channel, we are interested in the calculations under these topics. So the calculations we already covered part 1, part 2, part 3, part 4, and now we are going to part 5, which is electrical energy and power. But if you need complete notes, therefore in this book, Mastering A-Level Physics Paper 2, it has clear notes, worked examples, and trial questions on all these topics. So the worked examples in this book are the ones we are interested in on this YouTube channel. And if you need a copy, you can contact the author on any of these contacts or WhatsApp using this first one. A complete set of A-Level Physics contains 3 books. One is Physics Paper 1, another is Physics Paper 2, and the third one is Topical Question Bank. Then a complete set of Principal Mathematics is also 3 books. The one is Math Paper 1, Math Paper 2, and the Topical Question Bank. But if you do subsidiary math, it is only 1 book which you need, since subsidiary math is only 1 paper. So let's start our topic of electrical energy and power. So when electricity passes through an appliance, we usually call it a load, it develops and produces some heat, which may depend on any of the following. So the heat may depend on the resistance of the conductor, or the amount of current flowing, or the time for which current has been flowing. So resistance, current, and time. So the factors, so remember it has electrical energy and it also has power. So we shall start with this part of electrical energy. Energy or work done. So when a charge moves through a resistance wire, the work done becomes the electrical energy, which changes to heat energy. Therefore, work done is given by voltage times charge. Voltage is the same as PD, so PD times charge. So this is V, this is Q, and this is W. But you already saw earlier that Q is equal to IT. Q is equal to current times time. Therefore, when I substitute, I'll come up with W equal to V times IT. Therefore, this is one of the expressions for electrical work done. So if you have current, you have PD, and you have time, you can easily get the work done, or the electrical energy. Also, we already saw that V is equal to IR. So what happens when I substitute for V? I'll come up with IR times IT. So this I and this I becomes I squared. Therefore, work done can either be given in this form if resistance is not known, not given, or it can be given in this form if PD is not given. So sometimes they can give you current, PD, and time. So use this, or current, resistance, and time. So use the second one. Similarly, we know that I is equal to V over R. Therefore, when I substitute for I, I'll come up with V squared T over R. So in this case, if I is not given, you can use this expression. So you have seen an expression where R is not given, an expression where V is not given, and an expression where I is not given. So any of the three formulas, they all give the same answer. So in summary, electrical work done can be calculated using any of the following. So we saw this first expression, second one, and third one. The SI unit for electrical work done is joule, abbreviated as capital J. So when you're writing in full, it is small j. When you're writing in as a single unit letter, it is capital J. You must take note of that. Small j, here it is capital J. Remember, in physics, SI units must be correct. So a joule, by definition, is the electrical energy expended in a resistor of 1 ohm when a current of 1 ampere flows through it for 1 second. So all the units must be 1, 1. So R is 1, I is 1, and T is 1. That was the electrical energy. So we shall also look at electrical power. After looking at both of the formulae, we shall then go to the worked examples. So power is the rate of doing work, or you can say the ratio of energy the rate of energy transfer. Therefore, power is expressed mathematically in this way. Power is equal to work done over time taken, or power is equal to energy transferred over time taken, because of this word rate. Therefore, power, using this one, power will be W over T. We already know that W is equal to IVT, or W is equal to this, or W is equal to that. What does that mean? It means that power, while there is W, we shall replace it with where this W, we shall replace with these expressions. One with that, another one with this, another one with that, to get the three expressions of power. Therefore, using this here, power becomes IV. Using this here, power becomes I squared R. Using this here, power becomes V squared over R. The SI unit of power is watt, and abbreviated as capital W. Remember here, you must realize it begins with small w, and here the SI unit is capital W. Now, by definition, a watt is the rate of working of 1 joule per second. So with those, we shall go through the questions. Question 1 came from UNEB 1999, paper 2, question 4b, and it says, a battery of E.M.F 12 volt and negligible internal resistance is connected to the ends of a metallic wire of length 50 centimeters and cross-section area 0.1 millimeter squared. If the resistivity of the material of the wire is this, at what rate is heat generated in the wire? Rate of heat generated is power. So you know PD is that, length is that, you convert to meters, and also area is this, so it is squared. You convert it to meters squared, becomes, you multiply it by 10 to the power negative 6 to give you this. Then this is the resistivity, it was also given. So resistance of the wire is given by resistivity times length over cross-section area. So resistivity, length, cross-section area, to give you this as the resistance. Then the rate at which heat is generated in the wire, P, is equal to V squared over R. So in this case we have V and we have R. That means we use V squared over R. If we had I and R, we would have used I squared R. If we had I and V, we would have used power equal to IV. So any of the three formulas is okay. So when I substitute for V and for R, I'll come up with this as the power, or the rate of heat generated in the wire. Then question 2 came from UNEB 2020, paper 2, question 8b, Roman 2, and says, a 12-volt battery is connected across a potential divider. Remember, we already looked at a potential divider of resistance 600 ohms. If a bulb with filament resistance of 100 ohm is connected across 1/3 of the potential divider, determine the amount of electrical energy consumed by the bulb in 10 seconds. So here they want work done. So you first illustrate our potential divider. So we have our source, which is 12 volt. This is our filament of 100 ohm connected to a potential divider. They have told us that the whole of this resistance is 600. Therefore, the resistance of Rxy will be 1/3 of the total, which is 600. So that is why you say 1/3 or times 600 to give you 200 as the resistance of this part where the filament is, which is connected in parallel with the filament. Now the other one will be got by subtraction. So in a subtract, I'll come up with 400. So this is 400, this is 200. Now that we know the resistances, we can now get the total. So combining this resistance and this resistance, which is in parallel, we shall use special case of product over sum, and to give you this as the resistance of these two combination. Now when you combine these two, it becomes in series with this. Therefore the total can be got. But since we are using potential divider rule, we can easily get the PD, because when they're in series, that's when you can use potential divider rule. Therefore PD across XY will be this total resistance, which you have got as R1, over that very resistance plus the resistance in series. So that is potential divider rule. So potential divider rule was already covered on this platform. If you missed it, you can first go back and go through it. That's when you will understand this approach. So substitute for R1 and for YZ and for V to give you this as the PD across XY. After getting the PD, I know resistance, therefore I can get the energy. So energy will be V squared over R times T. V squared will be the PD across this, because they're in parallel, they have the same PD. Then the resistance and the time, which was 10 seconds, to give you this as the energy consumed. Then question 3 came from UNEB 2013 paper 2 question 8b, and it says three identical cells are connected in series with resistors of this and this. A current of 1.2 ampere flows in the circuit. When the two resistors are connected in parallel across the three cells in series, the current in the circuit is 2.2 amp. Calculate Roman 1 the internal resistance of each cell, and Roman 2 the E.M.F of each cell, and Roman 3 the power dissipated in the 3 ohm resistor for the parallel connection. So this shows that it is easier if you sketch. So we shall first sketch. The first case when the resistors are in series. So the cells throughout they are in series, but the resistors sometimes they are in series and also in parallel. So let's first deal with the case when they are in series. They told us when they are in series, what happens to the current? When they're in series, the current is 1.2 ampere, and when they're in parallel, the current is 2.2 ampere. That is why you are seeing us put here I1 equal to 1.2, because it is the total current from these cells through these external resistors. So total E.M.F, because they're in series, total E.M.F will be got by adding all of them. Add this, add this, add this, so we'll get 3E. So what we have done, we have let E to be the resistance, so the E.M.F for each cell, and small r to be the internal resistance for each cell. Remember, they are identical, so they all have E.M.F of E and internal resistance of R. So the total E.M.F will be good by adding the 3 to give you 3E. What about total internal resistance? Because they are in series, resistors in series are good by adding. So still we shall add the 3 to give you 3R. Then the total resistance, or the total external resistance, which is this. So these are resistors, but they are in series, so we will just add to give you this. Therefore, we know that E is equal to I in brackets capital R plus small r. Therefore, we shall come and substitute E total, I, R1 and R total to give you equation 1. So that has been the case when the resistors are in series. What about when they are in parallel? Remember, the cells, for them they are maintained, they are always in series, but the resistors, they are now in parallel. So we shall again redraw our circuit diagram to arrange them in parallel, and the current now changes to 2.2 as we saw in the question. Therefore, total E.M.F will still be the same, total internal resistance will still be the same, but the total external resistance will change because it will now be product over sum. To give you this, therefore E total is equal to I2 in brackets R2 plus small r. Then you substitute, and those will be two equations with two unknowns. We have two unknowns, which is capital E and small r. Therefore, we have to solve them simultaneously. When I equate, because they are all equal to 3E, when I equate the two, I'll come up with this. Then from there, you realize that we have only one unknown. Now, our aim is to make that r the subject. So when I open brackets on both sides, I'll come up with that. To collect like terms, I'll come up with, take this one this side and this one this side. Then divide it throughout by 3 to give you this as the value of r, small r. So that will be the internal resistance they wanted. Here the next will be the E.M.F of each cell, so they want the value of E. So you come as that from equation 1, 3E is equal to this. So where there is, in equation 1 was the other side, so where there was R, you have replaced with the value of R. And you have E as the only unknown. Therefore, make it the subject and it will be 5.39 volt. So now shall go to Roman 3. Roman 3, they want the power dissipated in the 3 ohm resistor for the parallel connection. So for the parallel arrangement, E total is so that E total is equal to this. So V is I capital R1. So when I'll come and substitute for R total, small r total, and E total, then PD will now be equal to 3E minus 3I to R. Then substitute for E, and substitute for I2, and substitute for small r. You come up with a PD as 4.125. So now that I've got the PD for the parallel combination, I can get the power using V squared over R. So substitute for V and substitute for R to give you the power they wanted. Then question 4 came from UNEB 2001 paper 2 question 10b and is edited. So a nichrome wire of length 1.0 meter and diameter 0.72 millimeter at 25 degrees Celsius is made into a coil. The coil is immersed in 200 centimeters cubed of water at the same temperature, and a current of 5 ampere is passed through the coil for 8 minutes until when the water starts to boil at 100 degrees Celsius. If the resistivity of nichrome at 25 degrees Celsius is this, find Roman 1 the resistance of the coil at 25 degrees Celsius, Roman 2 the electrical energy expended assuming all of it goes into heating the wire, and Roman 3 the mean temperature coefficient of resistance of nichrome between 25 degrees Celsius and 100 degrees Celsius. So we shall start with Roman 1. We are given that L is 1 meter, diameter is this, you change it to meters, and the resistivity is that. So resistance of nichrome at 25 degrees Celsius will be R25, which is resistivity times length over cross-section area. So this cross-section area is pi d squared over 4. So reciprocal will give you 4 over pi d squared. Then you substitute for resistivity, substitute for length, substitute for diameter. You will come up with a resistance as this at 25 degrees Celsius. Then Roman 2, they want the electrical energy expended, assuming all of it goes into heating the water. So when all of it goes into heating the water, what does it mean? So first of all, you shall come and get mass of water equal to density times volume. Density is that and volume is this, to give you the 0.2 kilograms. After that, electrical energy expended will be equal to heat gained by the water, because all the energy which was taken out from this went into the water. So this energy gained is equal to MC, change in temperature. So M is this, C is this, and change in temperature is that. You'll come up with this as the energy gained by the water. And because all of it went into heating the water, it means that electrical energy expended will be equal to this energy gained by the water. Then Roman 3 they said calculate the mean temperature coefficient of resistance, that is TCR, of nichrome between 25 degrees Celsius and 100 degrees Celsius. So also we know that electrical energy expended is equal to I squared RT, and this will be R mean resistance. They will substitute for this, substitute for this, and substitute for this. So this was 8 minutes, you have to convert to seconds. Therefore mean resistance will be 5.25 ohms. But we know that mean resistance is equal to resistance at 25 plus resistance at 100 over 2. Then we shall come and add the 2, substitute for this, and substitute for this to make this the subject. And let's make the subject, we'll come up with this. Now using this formula for TCR, we shall divide. It means that R100 over R25 is equal to R0 in brackets 1 plus 100 alpha over R0 in brackets 1 plus 25 alpha. Then substituting equation 1 and 2 into 3. Equation 1 and 2 into 3. It means that here this is equation 2, so this substitute here. And also you already saw that R25 is this. Therefore we have substituted, and now this one can also answer to come up with this. Then when I divide this, I'll come up with this. Now at this point I have only one unknown, so my aim is to look for ways of making it the subject. I'll first cross multiply, open brackets, collect like terms, and make alpha the subject. And that's what they wanted. So that brings us to the end of this video. Thank you for watching, and be reminded the next video will be on efficiency of an electrical circuit. So if you haven't yet subscribed, please click on the subscribe button below this video so that I can receive updates when the next video has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so we can all benefit as a family.